Hello, everybody. Thank you so much for attending today. We will get started right away here. My name is Albert Dunford, and I'm joined with Raphael, who will be covering the topics today. I'm just going to give a little bit of housekeeping. This session is being recorded, although I'm sure some of you will ask that question throughout if you missed the beginning. There is going to be some handouts that we can provide you with, the slides and the models Raphael will make available to you. What else can I call? There's a questions section. So I will be monitoring the questions while the session's going. I'll flag stuff for Raphael to cover where needed, but I'll do my best to kind of answer questions while Raphael is speaking. So please use the question tool. There should be a little floating thing for the webinar. So put your questions there. If you want to ask a question that's asked anonymously, or you don't want everybody else to know that you asked a question, please let us know in the question, and we're able to answer those questions privately so that they're not broadly known, broadly broadcast. So you can do that. Otherwise, yeah, again, my name's Albert. I'm a director here with the Global Technical Team. My specialty is power electronics. Raphael is in my group, and he's senior solution engineer dealing with systems integrations. And with that, Raphael, I will leave you to introduce yourself and get going on today's topic.
Perfect. Thank you, Albert. Hello, everyone. Thanks for your time being here. Okay, so a little bit of introduction. Let me tell you a little bit of what's going on here. I want to give you a little bit of my background and some announcements prior to starting. Then I want to set up the context of what I want to show you. I promise it's going to be interesting. I want to show you all the steps. What I'm going to show you is how you can accelerate your simulations using AI. And then I want to show you step by step how to do it. Then I want to discuss a little bit how to take it further. And then there's going to be some time for questions and answers. So let's get started. A little bit about myself. I'm part of Albert's team. As he said, I joined Altair in 2022, 3 years ago, and I'm part of a team that is sort of in charge of making sure that the customers get the most out of our systems integration products. I mainly focus on a lot of 0D and 1D systems modeling, that is either through scripts or either block diagrams. I have a lot of input on data-driven modeling as well as physics-driven modeling, including AI, and a lot of workflow automation. On my educational background, I'm an electromechanical engineer by my bachelor's, but then I focused on electrical engineering, and I was lucky enough to get the wave of the rise of AI just as it was starting, and managed to do a lot of applied AI for engineering during my master's. I'm based in Mexico, and I'm leaving here my LinkedIn profile in case you want to connect. Let me turn on my camera, as you already saw my picture. Yeah, that's good. So talking a little bit about news about PSIM. We're very excited, well, and for Altair as well. We're very excited that in recent weeks, the acquisition of Altair by Siemens just closed, and PSIM has come a long way since. It was founded in the early 2000s, and in 2022, the same year that I joined Altair, PSIM was acquired by Altair, and now we're very excited because there's no limit on the opportunities that will come being part of a company as huge and important as Siemens. So yeah, exciting times for PSIM and Altair. So this webinar is part of the monthly webinars we've been doing. The next webinar will be on June 12th. These have been focusing on things like reduced order models, automating optimization, coupling with other tools, coupling with other solvers in application areas like battery chargers, motor drives, grid connected systems, etc. And for the next one, I'm leaving the link here. As Albert said, you'll have access to the slides, so you can join and register from now. So enough introduction. With that out of the way, let me jump straight through it and show you what I want to show you. Here I have a model of a resonant power converter. Well, two models, in fact. This is a model that I built in PSIM. Right now, this is enclosed in another tool called to inactivate, but this is a model built in PSIM, and this is an AI surrogate model built with a tool called romAI. Let me run both of them. What I'm doing in this example is that the controller, the power converter has an external controller that is just changing the reference voltage that it should supply. As you can see, I'm simulating for 1 second only, and it's taking quite some time. I have here the reference control that it should match, the PC model, and the romAI model. Let me stop this because it's taking a lot of time, but let me show you how the real thing built with PSIM and the romAI model match. This blue thing with the ripples is the PC model, and the red one is the romAI model. It doesn't capture the ripples. But now let's see the real advantage. You've already seen it yields precise results. Let me turn the high fidelity model off and let's run again. And now it runs instantly. I can do many tests. I can run several times. And as you'll see, it yields practically instant results, less than a second. So how do I do this? This is what I want to show you during this webinar. How can we train surrogate models using AI that will give us accurate results and yet are going to take only a fraction of the time? So let me talk a little bit more about the technology that we're using here. The technology that we're using to build the actual reduced order model is called Altair romAI. And at a very high level, this is how it works. You run your high fidelity simulations and record the results of several runs in a training dataset. Then you use machine learning and state space representation theory and build a reduced order model from it. And what's the advantage? Once you have that, you will have a modular model that you can plug back into your system simulation and focus, instead of waiting on the simulation time to finish, just focus on the engineering side of things once you have the reduced order model. So again, why do we want to tackle this? Let me give you a little bit of context. Power converters are becoming more important every day with electrification everywhere. These things are coming many types, sizes, do many things like changing the voltage from a power source, changing its frequency, converting from AC to DC and the other way around, or from different characteristics of AC or DC. But I want to focus on one specific type. This is one specific type that we chose for this example, and that is resonant converters. These resonant converters are getting a lot of attention because they're very efficient and also they produce low electromagnetic interference. So that's two good advantages, very good advantages. But another reason why we chose them is because they are highly nonlinear and hard to control. So why did I choose this? Because if we can build an AI reduced order model from a highly nonlinear system, it would probably be easier to model some other kinds of power converters and to control some other kinds of power converters more easily, right?
So Rafael, let me stop you there, and I'm going to launch our first poll. And this is just going to be a little interactive stuff here, so you can click. There's let me hit launch here. So this is a typical, just asking what your typical application is. So go ahead and just click a thing on screen, and you can yeah, we'll hopefully see how things are going. So I do see how many people have voted. So if nobody's voting, then we'll just sit and wait for people to vote. So there's about a quarter of you have voted so far. Oh, we're getting good responses here. So just get in your last couple points, and we'll see what comes. And I think that should be enough. Okay, thank you so much for voting. Voting is closing in 3, 2, 1. Close. Okay, thanks guys. So it looks like about half of you are into high power motor drives, and the third are on lower power motor drive designs, and then some folks are on power supplies. So yeah, for the motor drive folks, yeah, we have played romAI models with motor drives, but yeah, and there's some comments on that in our community. But I'll let Raphael continue along here with the resonant converter application.
Perfect. Thanks, Albert. And thanks everyone for your responses. So yeah, we chose resonant converters for this experiment because they are highly nonlinear, hard to control, but they are getting more important every day. But then what's the problem? These things are controlled with very high frequency switching. For example, in the example I'll show, the switching frequency, the standard resonant frequency is around 200 kilohertz. So that's very computationally intensive to simulate. So if you're running simulations over long time frames, or if these converters are just not standalone simulations, but part of bigger system of system simulations, these simulations become slow, and I mean real slow, painfully slow. So because of that, any acceleration technique that we have that will save us time is very valuable, whether you're optimizing something, designing, validating, or integrating into a bigger scope of simulation, it's really valuable. In some cases, there's simplification methods that don't capture the dynamics, and that's good enough. For steady state analysis, you don't even need to delve into something like romAI. But if you're analyzing how the system responds to load changes, to faults, to whether you're analyzing different methods of control, then the dynamics are critical. And that is the challenge that you have to keep in mind for this session. This is what we want to do. We want to enable you we want to help you reduce the computational burden of your simulations while still capturing the dynamics. And in the end, how do we do it? Just as I showed you. We use a high-fidelity model created in PSIM to create the training data to train an AI model that is going to behave as a surrogate model, which in the end is going to have a very similar behavior. And I say very similar, I don't say the exact same, but just for what we need, capturing the dynamics of interest and running at a fraction of a time. For example, a similar simulation of a resonant LLC converter for running 20 seconds of simulation time takes in average more than 45 minutes for PSIM. But for romAI, it still takes less than a second. So I hope you already see the value in getting instant results here. Then before, let me remind you just about the speed of this. The model is predicting properly. When I say predicting, I mean the romAI model is predicting properly the results that the PSIM model is actually yielding. For example, you have the output voltage here, but also the output current. Let's look at this one as the scope is bigger. You can see that even though it doesn't capture, the blue one is the PSIM one, the red one doesn't capture the ripple that the blue one has. But if you have a better look at it, you'll see that the overall behavior is the same. So we can ignore that. We can sort of sacrifice that for having much faster simulations. And then again, the real value is when you turn the high fidelity model off and just get instant results. 1 second was simulated in 0.85 seconds, so faster than real-time results in this case. The tools that I'm going to be showing in this workflow are all part of Altair, and they're very straightforward to use. I'll show you at a high level what we did with each one of them. Well, the high fidelity model was created in PSIM. Then HyperStudy is a tool for creating design of experiments that I used for basically running the model I created in PSIM many times, changing the input conditions, changing some parameters, and changing most of all the reference control signal. So I ended up with all the files, all the results files from the simulation that I need for building a data set. And then I used Compose, which is a scripting environment very similar to MATLAB, for actually putting all those simulations together in a single, or in the data sets I need, in the format I need. I was about to say a single data set, but as you will see, We have a dataset for the training and testing, and another one in the end for validation. And in the end, I also use to inactivate to integrate everything, and also because romAI is a tool that is embedded into inactivate. To inactivate is a tool for systems integration and system simulation, which allows you to put together the high-fidelity PSIM model and the romAI model, as you're seeing right now. So with that out of the way, let me show you step by step how to get to this thing, how to get to this romAI model for you. The model that I started from, here it is in PSIM. It's a full bridge resonant LLC converter, and it's a very simple model. This is the converter itself, and to the right of it, there's a load, a generic load. There's an input voltage, and here on the bottom, you can see the control loop. It is a voltage control loop, and what is happening here is that I'm starting off with an initial reference, and then at some point in time in the simulation, I'm getting a change in the voltage reference. Let me run it and show you how the system behaves. In red, you can see the reference voltage. I used a low pass filter to make it easier for the system for reasons that you will see later. And well, it follows the new reference when it occurs. There's a reference here, the reference change happens and it adapts. The input voltage is constant and the system changes its switching frequency, and as a consequence, the output current and the output voltage change to match our needs. So this is the real thing. This is the high fidelity model. Now that I have this model defined, I jump to hyperstudy to build the design of experiment. I'm going to select the PSIM model that I'm going to run, which I do here. It's the model that I just showed you. And afterwards, I choose the variables that I'm going to explore over. Basically, it's going to be the input voltage, the voltage that is over here in this source, and the initial voltage reference, and then the reference voltage step. That is the initial value that it should provide voltage at, and then how much it's going to change. I have some other values here which I use for controlling the simulation, like the time at which the change is going to happen, the total simulation time, and when I will start printing the results for my results file, for the dataset, for reasons that you will also see next. But I only vary these three things that I showed you: input voltage and the actual reference that the converter is going to have to follow. There are some constraints for this to make sense. I've set up some limits myself. The nominal value of the output voltage is 420 volts. So I'm making sure that the upper bound and the lower bound is respected on each different simulation, that even with the voltage step, we don't exceed that limit. And I also put a lower limit on the minimum size of the reference change. I do not want a reference change that is negligible, so I put a minimum value of 5 volts. With that, defining the conditions which we're going to explore over, basically what you're ready to run as many simulations as you want here. There are some required steps, that's testing the model. A hyperstudy asks me for an output response. That is something that it is going to be able to read from every different run, but I just have to put that as a requisite for hyperstudy because I don't need it. What I need is to run many simulations, so I have different results files for different conditions. So once I have all this set up, I just create my design of experiment. This is it. I choose the method that is going to be used for creating the different dots over the dimensional space of the DOE. I select the number of runs. I want 50 runs. I use 50 runs for training this romAI model. And afterwards, I can evaluate whether there's an option for executing 10 simulations at once. I can set it to the number I want, whatever it is. 10 is a good number. This takes less than 2 minutes. And you will see, let me expand these columns. You will see that each column here is a different PSIM simulation that is going to get executed. with different input voltage, initial voltage reference, and reference voltage step. Ignore this column as it's just the response that I needed to define for hyperstudy. But now I have my full space of 50 simulations running from the same system. What do I do? Because now I have them in this way. Let me show you. I run a DOE, and this is the DOE. I have a directory for each run with the model and the corresponding results files. But that's not useful for me until I have it all compiled in a single dataset. So that is what I used Altair Compose for. This is Altair Compose. This is a scripting environment similar to MATLAB that I mentioned earlier. And I'm basically using it to go from here, the DOE containing all the different simulations, to a single CSV file that looks like this. This simulation, this dataset, sorry, has only the signals that I need to train the reduced order model, and they are put one after the other. There's many simulations one after the other here, so this dataset is pretty big. I think around 50 megabytes, pretty big for the standards of a CSV that would handle results files for PSIM, because it's not huge in other ranges. But here you see that I've also plotted the signals just as a sanity check. The script is very simple. I won't delve into it, less than 100 lines. But what it's basically doing is detecting all the results files in the different subdirectories and writing everything either in a training and testing dataset or a validation dataset. There's 50 runs in total. I decided to keep 20% of them as validations, as part of the validation dataset. So we end up with 2 datasets. But here you will be able to see I'm plotting just as a sanity check. It's not needed, but I want to make sure that the results that I'm training the surrogate model in make sense. Different runs have different voltage reference signals that in turn make the converter behave in a different way. And there's 50 of these. Once I have compiled them in the dataset, I can jump back. Well, I can get started with the actual training of the AI model. I'm back here into Inactivate. This is the tool that I showed you in the beginning, but I don't want to run this model right now. What I want to show you is this thing called romAI Director. romAI Director is a tool. I had a session open here. Okay, romAI Director is a tool that is going to be used for training the actual reduced order model using AI. So it consists of 3 steps. First, pre-processing the information, pre-processing the data set for us, defining afterwards the model, building the model and training it, and afterwards analyzing the performance. So let me show you step by step how that is done. I'm going to import the data set that I used. There's one called TT validation and another one. Another one is the one that I'm going to create right now. So let me select the one called TT for train and test. It's getting imported. And I have it here. You'll be able to see that all the different runs are present here. 40 segments for training. What I want to do here is to filter some of these at any, in this case, I want to filter them at 20 kilohertz. And what's the reason? Look at this. The high-fidelity model contains some ripple, but I don't want to train romAI on that ripple. I want to just train it on the filter signal. You can see the green one overlapping over the blue one. This one doesn't contain a ripple. So I'm going to do that for all the signals that have this ripple. Not all of them have it, because some of them are constant, some of them are control signals, some of them I don't need to. So once I have that, I can export it, which I already did, and use it over here. It's the one that says 20 kilohertz at the end. It's the same data set, but filtering out the ripples that I don't need for training. So now it's getting loaded, and automatically romAI Director detects all the inputs, outputs, and states. And I'm going to show you what all of those means. Inputs are the things that are going to get fed into the surrogate model. as you can see here, there's reference voltage and input voltage in this case. Output is the things that are going to get produced by this model. In this case, output current and output voltage. Though no, let me look properly. Yeah, just one output, and then we calculate output voltage. I'll get into more details about this later, but yeah, some inputs, some outputs, and some internal states. Think of this always keeping in mind state space representation and dynamic systems theory. So let's choose our inputs: input voltage, output voltage, and the actual control signal, because we are simulating an open loop system. We don't want to abstract the controller away. We want to control the system with the exact same controller that we control the high fidelity system with. So switching frequency is a controlling signal, so it's an input as well. The outputs I care about are only output current, and I'm going to declare this one as a state. That is, it is an internal state of the system that has to have a continuous value, and it's going to dictate the dynamics of the system depending on its inputs. So just a little bit of a refresher about systems theory. In a dynamic system, if you have knowledge of the internal states of the system and the inputs, you can predict the output, or you can calculate the output of the system. So once that is ready, I'm going to choose some parameters, the architecture of the neural network to use. These things need to be small. I know for some other context, and once I was guilty of trying to use very big models, very big neural networks coming from other background. In some applications, you need colossal models. But here we're using a neural network that has 2 hidden layers. It has 20 neurons for each layer. It's activated with ReLU function, and I'm going to train it. Well, I'm going to train it for 200 epochs. I'm going to save snapshots of the model every 50 epochs, and I'm going to, as there's a lot of data in my data set, I'm going to just keep a very small fraction of it for testing. What that means is that I'm going to iterate over all the simulations I have, and then a small fraction of it is going to get used on each iteration during training for scoring how the model is performing. I'm going to train it. Yeah, sorry, Albert.
Sorry, Rafa, I was going to interrupt you here. There's a question which I think is relevant to what you're talking about right now, which do you see in the question tab from Ranjan about the state-based systems and the linearity of it? Do you know the answer to that question?
Let me have a look.
So the question I'll read out, state-space systems are linear. I assume these are modified state-space systems that use neural networks.
Yeah, exactly. I intend to delve a little bit deeper on the theory of romAI a little bit afterwards, but for anyone who is already curious, the technique is called deep state representation. So you mix state-space theory with neural networks to not replicate the response itself, but replicate the math behind the system. Yeah, so I'll give a little bit more detail of what is needed and what is needed and what the user needs to know. But yeah, I hope that's enough.
Yeah, keep going. I'll monitor the chat.
Perfect. That's good. So okay, yeah, as we said, we're defining the characteristics of the system that we are going to train, and very small neural network needed for this. I'm going to train it for 200 epochs. What does that mean at a very high level? 200 times I'm going to loop over all the data set, adjusting the weights and the biases of the neural network for it to make a good job at predicting the result that I want. Even though I'm training for 200 epochs, every 50 epochs, I'm going to save the model. It's a good practice because in the end, you'll be able to see the model and how it performed after 50 epochs, after 100 epochs, 150, and 200, and you can pick the best one. That way, you will not be subject to overfitting. You won't have the problem of performing too well on the data it sees, but not performing well enough outside of the scope or a new simulation. So yeah, that's it. With that, well, I would just need to select an output location and the name for the reduced order model and click play, and it would start training. This takes a little while. In this case, I would guess a bit less. It's a big data set, so a bit less than 30 minutes. So I'm not going to go over it right now, but I'm going to show you now how the model I trained performs. I'm going to use this data set now for analyzing the results and seeing how the model works. Why? Because this is totally fresh data. I trained it with 40 simulations. Well, I created a data set with 40 simulations for training. I filtered out the signals that had ripples. Then I kept another data set with 10 runs just for testing afterwards. And now let's see how it goes or its performance when talking about this. When analyzing or when you finish the training of a reduced order model here in romAI, the post-processor tab is going to load automatically, and you'll be able to see this plot first. This is the loss and how it was reduced over all the epochs. Remember, I trained for 200 epochs, but in the plot I'm seeing here, the ROM that I chose, the one that performed best, was only trained for 50 epochs. That's not always the case, but I always recommend saving snapshots just to be sure and be able to pick the best performing one. And in the end, the loss was steadily decreasing, and in the end, there was a test loss calculated on the actual results after the model was trained. But always, when I'm using this tool, that its purpose is to run system simulations, what I found more useful, more than metrics, is just looking at how it would perform compared to the real thing. So now I switched over to time simulations here, and I have the 10 different simulations that comprise the validation data set. And you see in green the real response that it should have responded to, and in blue it's the actual response from the AI model. You see that sometimes it's almost identical, sometimes it has slight changes, sometimes it might even do a poor job. Let's look for the one that performs the worst. This one doesn't perform really well. Now, what do I want to highlight here? That this is not magic. Not that I think that this is not a useful tool. This is an amazing tool. I love this thing. But and as you'll see, we want to have something that captures the dynamics at a well enough level, because when you plug it into a bigger systems integration, all of these discrepancies go away. If you capture the dynamic behavior well enough, you're going to be able to do what you want to do. If you have a look at this y-axis, well, the difference is minimal, right? Less than 1 ampere in difference, and this is the one that performs the worst. And well, I have to clarify that I've trained this one properly. You may end up with some models that do not capture the dynamics properly, but that's why there are some guidelines that I want to share with you to ensure also that even though this is not magic, it's an extremely useful tool that you will love if you use it appropriately. So once I have the model ready, what's the next thing to do? The model is ready here with the results, but you will end up actually with something that looks like this, a folder. And that is when you're ready to plug it into a bigger system simulation. Let's jump back here into Twin Activate and let me show you how that is done. Let me click into this system, and this is the surrogate model that I've trained. Once you have your model, you put in a block like this in Twin Activate and you select the folder that contains the surrogate model that you just trained. As you will see, it has an independent controller from the high-fidelity model that is exactly the same as the other controller. So both the high-fidelity model and the surrogate model are controlled with controllers tuned exactly the same. And you will see that there's also a small PSIM block over here. That is because this model predicts the output current, but to predict the output voltage, I'm still using a very small much simpler PSIM model that just given a current calculates the voltage. So that's very straightforward. On the other side, the full thing, the full PSIM high fidelity model is here, the thing that I showed you in the beginning. So that's why we have the high fidelity on one and the reduced order surrogate model here on the other one. Let me refresh and run again. Now you have a little bit more context of what is happening here. I've explained how to build the reduced order model, and as we discussed earlier, you can see, is this perfect? Is this a perfect replica of the high fidelity thing? It's not, but for a systems level model, maybe it's what you care. If you're analyzing how it responds to a fault, if you're analyzing over, I don't know, if you're analyzing battery charging, or you want to simulate over longer time frames, all of that becomes extremely valuable. Let me zoom in once again. Let's now do it on the switching frequency. Remember, the switching frequency is getting created by different controllers. They're tuned exactly the same, but acting on the response of the different systems. And you will see that ignoring the ripples, otherwise, it's matching very, very well. And then again, if I turn it off, instant results. That's the real value of romAI.
So Rafael, let's just pause for a second. I will launch another poll.
Perfect.
So folks, there's another poll on the screen. Click the dot. Oh, this should be. Please select one. Yeah. So. Okay. Everyone's clicking a little bit faster. Okay. So I'll close the poll in about a couple seconds. You're voting. And okay, thanks guys. We saw out a third are in power hardware design. Systems is in range, then thermal, then magnetics, then worst case optimizations types of stuff. So thanks so much for voting. And there's one last poll which we'll do a little bit later on, but I'll turn it back over to Rafael. I think Rafael made a great point just there where it's an identical controller to the high fidelity system controlling the reduced order model or the surrogate model, which I think is very valuable.
Yep, perfect. Thanks, Albert. So yeah, as you see, you can use the same controller to simulate the reduced order model and get much faster results. And well, in this case, it's a simple side-by-side comparison simulation, right? But we have done a lot of tests for exploring the capabilities of romAI fully. So now I would like to talk a little bit about some other things that we've tried, some lessons we've learned, some good practices we've learned, and very importantly, what we are trying to do next. These are some of the things that we have expanded for. Talking about battery charging using these converters, it's common for more than one converter be used to charge a battery at the same time. So we trained reduced order models to charge in a parallel configuration. The plots that you see here, I built training a romAI model from something like this, one parallel converter here, another here, charging the same load. And what you end up with, let me open it over here. What you end up with here is something that, well, we have side by side the two romAI models that represent a converter each, and we have the high fidelity thing over here. And you end up with something that, again, doesn't capture the actual ripples and the sort of fight between the converters to provide power. But in the end, when you add them up, you get a very similar behavior. Look at how similar these things are. And again, if you turn it off, instant results. Oh, this one, I shouldn't have clicked again on the past one because now it's simulated again, but it was a funny thing in which sort of one of those reduced order models diverged. So I wanted to highlight that as an example of how this is not magic. This is sometimes going to provide results that are not actually accurate to all general applications or scopes of projects. But what I mean by that is you cannot train a reduced order model to capture all the dynamics and to capture at 100% fidelity this thing. If you did, then it wouldn't be a reduced order model. So the thing is, keep it constrained to the things that you're interested in, and you're going to be able to predict results much faster at a good accuracy. What other things have we explored? Well, in this plot that you see to the right, the one to the left is the one that I just showed you, but the one to the right is one in which I coupled not only the output side of the converter, and I predicted not only the output side, but also the input side, sort of to couple, to make it an equivalent circuit of the providing the accurate dynamics to both sides of the converter. And I also used PSIM's thermal module to predict the thermal losses. Let me show you how that runs. You will see that there's an initial divergence. Just as if you've been looking thoroughly enough, you have noticed that there's always an initial divergence. I'll explain why that is the case next. But afterwards, it performs really well. I'm simulating for 200 milliseconds. You see the results match very closely both on input, output voltage, and the thermal losses. And if I turn it off, again, instant results. You can see that it takes a little bit of time for the output current to actually match the reference because there's this initial divergence that I'll mention. But yeah, I hope you can see the value. This one was built from a converter using PSIM's thermal module, as I said, more complete integration. And in this case, there's a very important thing going on. It is that we're separating tasks between romAI models. One romAI model is in charge of producing one of the predictions. That's a very good tactic. You can bundle these things together. You can put them sort of in series even, and you can build more complex model, far more complex than what a single romAI model would allow you to do. So, okay. I've already mentioned this in a question that we had earlier, but this is the theory behind romAI in a nutshell. It's basically mixing machine learning and dynamic systems theory. As I said, the technique is trying to use neural networks to represent the actual dynamic and the underlying math of the systems that we want to model. The user just needs to know, with the slightest bit of systems theory, you have to know which signals are your inputs, which signals are your outputs, and which are your internal states. This might be the trickier question because there's no single possible answer. And then building a very simple neural network, and I showed you again, very simple, 2 hidden layers, 40 neurons in total between those 2 hidden layers. romAI builds a model that captures the underlying dynamics, and that has 3 huge advantages. The first advantage is that you're not predicting the response itself. You're not matching the response that you trained it on itself. You're instead matching the underlying dynamics. So because of that, you're going to be able to run extended time simulations. You already saw that, or if you didn't see, the simulation I showed you at the beginning, the original converter I showed you the process of, and the results, these were simulated for 30 milliseconds. but I can easily simulate for more than that, for 200 milliseconds, 1 second, 20 seconds, because romAI captures the dynamics, not the response itself. If it captured the response, it would struggle simulating farther than what it was trained for. Another huge advantage is that it can perform well. It can perform well without using a huge data set. So other traditional approaches would require lots and lots and lots of different simulations, varying parameters slightly, to give this impression of a continuous space of parameters. So the huge advantage of this approach as well is that you don't need much. Creating my dataset took less than 2 minutes or less than 3 minutes to run, because I ran 50 PSIM simulations. And with that 50 PSIM simulations, I took 10 apart for validation, and with the remaining 40, I used it to train. And that was good enough. Other approaches would require far more data. And the last advantage, which is also huge, is that it performs really well both inside the design space and also outside. You can extrapolate the conditions on which you trained a little bit, and it will also perform well enough. Again, it's not magic, so you cannot extrapolate infinitely to totally different conditions, but to some extent you can.
So Rafael, there was a question, and maybe I answered it incorrectly there. The last one there from Anand, can we build digital twin model to predict target variables by combining simulation data and test sensor data? And I mentioned that we could mix test data and sim data for sure, but I was a little bit more hesitant about the predict values outside the trained data set with regards to that extrapolation. Maybe can you expand on that comment a little bit more?
Yeah. Well, as I see the question right now, let me address that. It's another common application to, instead of trying to predict actual outputs of a physical system in the world, sometimes these things are used as observers. We can estimate internal states of the system. So I mentioned that because you can turn around romAI in clever ways to give you exactly the information that you need about a system. But also, as I said, this doesn't predict the actual output itself, but the underlying dynamics. And if you have the underlying dynamics, you're going to be able, let me put it as an example. Here, I trained for an output voltage between 440 and 400, if I remember correctly, because its nominal output voltage is 420. I would still be relaxed when testing over 445, 450 maybe. Would I test low output scenarios? No, I wouldn't. I wouldn't test, I don't know, no load scenarios. I wouldn't test input voltages far below 1/2 of what I trained it with, things like that. But it's commonly used for training outside the scope. And importantly, if you plug it in optimization workflows, you can even try to replicate the target behavior as a target behavior that you want to replicate, and get the actual parameters that you need.
So
hope that
Rafael,
answers.
Yeah, I think a little bit more about his question now, and I think I understand exactly kind of what he's asking. And there was an application note that we published a little while back where we used a romAI model to replace an observer model in a sensorless motor drive application. I'm not sure the feasibility of that long term with regards to the computational burden of that romAI model deployed on like an MCU or something like that. But yeah, we were able to close loop with a romAI model providing the rotor position of that motor. Other applications that definitely could be looked at is, say you wanted to predict, say the heat of a device. So we could have a transient romAI model, or we have other modeling approaches where you could say have a model of a heat sink and try and predict what temperatures would be like in that system with this surrogate model. So yeah, you could use romAI as a surrogate model to provide information that would be hard to observe otherwise. So yeah, I hope that answers your question a little bit more, Anand, now that I think a little bit more about it. But yes, you could use this as a digital twin to predict what a sensor would provide. So instead of having that sensor, you would have a surrogate model providing that information instead. Does that answer your question now fully, Anand? And while he's typing, I'll let you keep going, Raphael.
Yeah, perfect. So yeah, romAI very widely used for digital twins as well. So again, good practices that we've learned along the process. I'm finally going to address the small divergence that you see at the beginning of simulations. So again, iterating for the 100th time, this is not magic, and you have to make the job for romAI as easy as possible. If I started training from t equals 0 of the simulation time, when the converter ramps up, there's a spike. Here you can see a spike current coming from the real, well, from the high fidelity model, and then it settles and follows the reference. It was way harder for romAI to capture both the initial transient and also the spike, the initial spike. So because of that, I decided to trim all the results before 2 milliseconds. So this line you see here, everything before this line was ignored for training. And you can see then that that's why it takes a little bit of time. I think I used another approach for this one that models losses, but let me jump to the one I showed first. Let me turn it on. This is the one I showed you the workflow, the full workflow. Let me stop. You see that before 2 milliseconds, there's a slight divergence between PSIM and the high fidelity, PSIM and romAI model. So that's why we didn't include the initial transient to make the training easier. Then again, this is something that is totally feasible if you're interested in the behavior as you have started. If you're analyzing simulations which are already at a steady state, and then you're analyzing faults, changes in reference, whatever. There's also a good trade-off here between the time frame to simulate for and the training duration. You have to keep that in mind. The shorter the simulation time, the training is going to be faster, but that might not capture the dynamics that you want well enough. Maybe you have to have a lot of time being settled in a steady state for it to capture how the system performs when it is a steady state. Small models should be used. I already mentioned this, so I'm not going to delve so much into it. But the rule of thumb, there's several rule of thumbs, because the good measure to keep between layers is 2 and 4. For neurons per layer is 20 and 40. But there's also another rule. In machine learning and deep learning, especially, these rules are not fixed. Always feel free to explore further than that. But always I recommend for starting something like a model looking like this. Don't try to overtrain it for 2,000 epochs, 3,000 epochs, just maybe maximum 500 epochs, but always, if possible, save snapshots, because you can get surprised how some models perform really well when trained over a low number of epochs. And yeah, again, simplifying the task. Maybe you have noticed that all the references that we give here are sort of filtered down. They are not hard reference changes. It was much harder for romAI to be trained on hard reference changes, but once you have it trained for smooth reference changes, you can test how it behaves on harder reference changes, or even on conditions outside of the main intention of the training or the main experiments on the training. What I mean, well, validation data set, as I showed you already, is a good practice to evaluate how it goes, how it does after you train it on totally new data. So create that one as well. But let me show you what I mean by testing it outside of the scenarios that it was trained for.
Raf, before you do that, let me just launch the last poll, and then also remind people we're approaching end of time, so please start thinking of your questions. So let me launch the last poll here, and oops, well, I double clicked it. Oh gosh, never mind. We had one last poll, but I mislaunched it. So, but yeah, please start thinking of your questions. We've got a few minutes left on the session, so yeah, Raf, keep going here, and then we'll.
Yeah, perfect. This is what I wanted to show you. This is the exact same model that I showed you how to train side to side with a high fidelity thing. But what I'm testing here is a sudden step in input voltage. And as you can see here, this is something that it was not trained for at all, but it does a really good job at sort of capturing the correct dynamics. So always keep that in mind. Even though results might seem a little bit tricky over here in the window that you'll see when you're evaluating the results, implementation in system of systems tools like TwinActivate can allow you for expanding further on what you trained the system to do. Last, apart from the good practices we've shared, there's some principles that we've learned. We were able to train models in open and closed loop systems already. The parallel converters that I showed you were trained in closed loop, that is capturing the dynamics of the controller as well. So these models just follow the reference that you give it. We have found out that there's good practices for choosing the internal states, mainly the switching frequency if you're simulating closed loop systems. But if you're simulating open loop systems, the output itself is the best thing that you can choose. As I just showed you, there's other conditions like abrupt input changes that you can test in those simulations, even though you didn't train it explicitly for that. But yeah, you can see that we've done a lot of things, and we encourage you to go try it for yourselves. And there's a lot of things to still finish defining. What's the absolute best way to model this? Closed loop, open loop, probably depending on your needs. Which signals to take as inputs? Which structure for the neural network would actually be the best one to use? What's going on with the starting transient, and how can we manage to capture a reduced order model that is able to perform well on both? Those are things that we're still working in. The optimal data set size, we can make it smaller and it probably would work and accelerate the training. We could probably make it bigger as well. What's the optimal time step? And yeah, there's a lot of things to be explored, though there's a lot of good results that have been obtained from romAI for power converters already. And there's next things that we want to try out, namely putting more realistic input converters like PFC converters as sources for these reduced order models that we're creating, involving these in bigger system simulations with lots of converters, different kinds of converters being modeled as well. So yeah, exciting times for romAI and power converters, with lots of opportunities for things to try and accelerate your simulations further.
So Raf,
with that,
there's a question for you from Ignacio in the chat. If you want to read it out and then answer.
Perfect. Hello, I have two questions. The first one is, if you can explain again the concept of state variable when selecting the signals for training the ML model. Well, the state that you have to choose is any internal state that you know about your model that shouldn't change. Shouldn't change abruptly. That should be a continuous signal. Because given state representation and dynamic systems theory, as long as you know your internal states and the input at any moment, you know the output. So it's anything that is going to, and this has to be chosen sort of trial and error if you're not sure, and testing around many different configurations. But anything that is going to have a continuous or should have a continuous signal as its behavior and gives you a little bit of insight on what is going on about the system, then it's a good choice for choosing as a state variable. There could be several state variables as well. And addressing the other question, as far as I understood, the ML model you used is a fully connected model with only inputs and outputs. So I don't know, what do you mean by states? And my second question is if you can use recurrent neural networks for the reduced order model. Okay, the state, again, iterating, is a sort of signal, specifically talking about how romAI uses it. It's a signal that is going to get used for scoring and has to keep a continuous behavior. And when I say scoring, every iteration during training, it's getting tracked as well, and it's getting associated with the inputs and the outputs. And about using recurrent neural networks, it's not possible. This is a different technology. As I said, it mixes neural networks and dynamic systems theory. So it performs way better than recurrent neural networks because that has been used already. Hope that answers your question, Ignacio. And with that out of the way, I just wanted to leave you with these resources that are available in the slides I shared. These are community articles that we posted for doing these things yourself, more detailed walkthroughs, and introductory e-learnings to the tools that I've showed in this session. But that's all from my side that I wanted to show you.
Okay, thank you so much, Rafael. As I mentioned before, this was recorded. The recording will be posted on YouTube and will be linked. Thank you so much for attending. Any further questions, please reach out to us. Happy to help. Yeah, thank you so much, guys.
Thanks everyone for your time and hope this was useful.
Now I just need to remember how to turn off the the session.